So let's see how to simulate the typical 3D solid mechanics NAFEMS benchmark, the LE10. So this is how it looks like. A 3D solid piece with various constraints applied and a Z directional load. And then we will be interested to check what is the value of the YY stress component, which should reach minus 5.38 megapascal. We create a project, we import the step file. Then we apply materials. So we could select, for example, aluminum to start with, and then we will change the material properties to match exactly what's in the NAFEMS benchmark. So 0.3 Poisson's ratio and 210 gigapascal Young's modulus. Now this whole piece is this material with modified properties. Now we're done. We can move on to the physics definition. So we will use normal solid mechanics. In steady state, it applies on the whole region. Now we have a couple of constraints. So the first constraint is applied to the surface over here. It targets the Y component of the displacement only, and we set the Y component to 0. Now the second constraint is applied on the face over here. It targets the X component, and the X component of the displacement is clamped there. Third constraint applied over here. This targets both the X and Y components, and they're forced to be equal to 0 over here. And the last constraint is applied here, and at that region the Z component is forced to 0. Now as a last step, we need to add a load. Now the load applies to the top surface, and it is in the Z direction, and the magnitude is minus 1 megapascal. So that's it. We can move on to the simulation. So let's mesh. We could ask a bit finer mesh with refinement where the curvature is higher. Now this mesh is artificially chosen to lead to around a bit more than 1 million unknowns. Now we will also want to see the displacement field U everywhere, and we can already prepare the script to output exactly what is required by the NAFEMS benchmark. So this is what is required. So we have the elasticity matrix H here in this Python scripting interface that has been automatically generated based on what we have defined in the graphical user interface. We have the elasticity matrix H, the strain tensor in void form, and then the product gives the stress tensor in void form. So if you want the YY component of the stress tensor, then it's the first component of the void form. And we will interpolate it at 2, 0, and 0.3 meters in the X, Y, and Z position. And then we will print this, and we'll make sure that it's close enough to the 5.38 megapascal of the NAFEMS benchmark. Now the mesh is finished. We can visualize it and notice that it has indeed been refined where we expected it to be finer. And we can start running the simulation. So we could use, for example, to accelerate a bit the simulation, use 50 nodes with each one course. And we're ready to run. The mesh is loading, and we will use domain decomposition to simulate this 1 million unknown simulation on these 50 nodes. We use a quite strict tolerance. This can of course be sped up, but it does require a little manual effort. In any case, we are at 5.41 megapascal, so really close to the NAFEMS benchmark value. Of course, it depends where you refine the mesh, but this has run in 13 seconds, so something absolutely decent. We can visualize the results, so we could want to see the displacement field. There it is, and we might want to warp this. There we go, the warped solution. That's it for this video. Thank you for watching.